here too. All right, great. All right, well, apologies for the week's delay, but as you'll recall, we were looking at WASP 43 on the night of March 28th, and when we looked at the image lab, you'll remember the data got messier at the end because the star was actually setting at the end of the run, and so it was a little messier at the end. And we did some of that interpretation of the raw data back in webinar 2, but now we want to look at our final light curve here as a group. And the data lab allows you to kind of take a look at this, and as we go to page 2 of the data lab, one of the things the teacher guide will lead you through, and I just you can actually have your students make an estimate of where they think the duration of this, they can click and drag where they think the duration of the transit actually was. It's a little hard for me to tell where it actually starts there, isn't it? It's a little hard, but maybe. And you can see this is a very short transit. It's, you know, just a little over an hour, maybe an hour and a half. So we have a very short and pretty deep transit. The other thing the data lab allows students to do as they're first looking at their final class data is to show where astronomers predicted the transit. And I'm clicking this on and off here. And so you can see our data agrees pretty closely with the astronomers' prediction of when the transit should take place, although it appears to me, at least from our messy data, our transit begins a little earlier than the predicted. The other thing you can do is show the data from another epoch, another night when WASP 43 was transiting, and students from the ExoLab, and this is data from other students. So again, our data is somewhat in agreement with that. So even though this might be your first light curve and you're not sure, am I really seeing a dip there? We have several lines of evidence. But the key thing the data lab has on page 5 is this model fitting tool. Oops, actually it starts on, let's go page 4, on this model fitting tool. And you'll remember that our model is a simplified model. We just have this idea that there's a star with a constant brightness, and then a period when the planet starts crossing in front of it and it dims until the whole disk of the planet is in front. Then we're during transit, and that's a symmetrical model, and then up again. So this is a simplified fit, and you know, it's a little hard to say, but maybe that would be my eyeballing a best fit. And then on page 5, we give you a little bit more of an analytic tool to find the best fitting model that fits this data. And that, as I start to now move the green, red, and orange legs of the model, you can see all these little thin gray lines. And so what our model is calculating is the sum of the distances of all those data points from the model, and we're trying to minimize that to get the best fit. And so you see you have a little score here, my best score, which is really showing you when you've minimized the fit. And so that's pretty good. So although it's not as good as my best score, so let me reset to best. There we go. Can I get better than 404? I can. Okay, so a little higher. A little higher here. And so I can play around, reset to best. So maybe I could get even better than that. This is really just an indication of when we've minimized the distance from all the our real data points from our model. And so this is our best fit model that shows a little more than a 3% dip. So that's a pretty big dip in the brightness of the star. You can read the percentage over here, or you can calculate the percentage over here, and you'll notice that our model also has an uncertainty estimate as well. This is kind of twice the standard error, or the 95% confidence level that's being calculated here, assuming that our variation is random. Jim, I thought I just recently talked to Roy about this, and he was, there's two, of course, there's a couple ways of calculating our error here.
Actually, Roy's here, and he said he'd be happy to jump in.
Yes, please jump in, Roy.
Oh, okay. I wanted to jump in about something else, but while we're on this, so the error, there are different ways. There's no unique way to calculate the best fit of a curve. This one uses the least squares that we're basically just looking at the distance of every point from each segment of that line. In other words, from the nearest segment of that line, and then doing the least squares, which is squaring that distance, dividing by the number of points, and taking the square root of that. And what that does is to basically, the more points you have, the less error you have. And what that's saying is that the more data that you have, the more you can trust each point not to be the actual natural value, but to be the one that would occur if you did this experiment over again, and if the data were affected just by chance. So whenever you see that, where they say, well, it's the error or the standard error, they don't mean it's the error from the actual value. They mean it's the error away from the value that's given by your data and taking the mean. Does that, let me say that again in English, okay? In other words, the assumption is that the scatter in the data is caused by chance alone, and that it's a normal distribution, a Gaussian distribution. It's like flipping a coin. Sometimes it'll come up heads, sometimes tails, that sort of thing. And that assumption, of course, is not true because, as you pointed out, as Mary was saying, well, there is the moon to contend with and the air masses and so forth. So those will affect the data in a way that's not random. But the error here that we're calculating is looking just at that scatter, and it's ignoring anything that might be not random, because the statistics don't know anything about nature, and they don't know anything about the moon or anything like that. So they're just looking at the data that you give them, namely how much scatter is there and how many points are there. And based on those two things, it's going to tell you, well, you know, if you did this over again many, many times, this is where this is where the data are likely to fall. And the error that we give there is basically two standard deviations, meaning that 95% of the time the data will fall within this average and the error 95% of the time. So if you give it,
so plus or minus 0.03 in this case is going to be, you know, it's going to fall between here and here.
Yeah.
Right.
The thing I just wanted to mention before you pass by it, because it's really quite evident here. I was just reading the comments of several dozen students who had worked with a star that's not WASP 43, but is very similar, has a very similar curve. And one of the things that disappointed them when they looked at it beyond the scatter was that it seemed as though the transit came down very quickly and then moved right back up again. And they said, well, that doesn't correspond to what we thought would be the model. We thought there would be a dip, and then it would stay leveled off for a while, and then it would come back out. So I just wanted to make explicit that you get this sort of V-shaped curve when the, and I don't know, Mary, if you're going to go on to that in the later pages, but you get that V-shaped curve when the planet is just grazing the star. So it's, yes, it's passing in front of the star, but almost as soon as it goes across it, it's now coming out the other side, rather than going across the biggest diameter of the star. And what Mary has done with this model here is, so she's imposed a model that does have a straight line at the bottom. And students may wonder about that and say, well, it doesn't look straight to me. So we're imposing one because we know, we're saying that's our model, that, you know, no matter how fast it may, no matter how much it may graze the star just barely, for some period, it's going to have that little line down there. So, so you may want to make explicit to your students that you're imposing a model on the data. And then later on, you'll see that in I think a few pages later, you'll see that that model does correspond to a grazing transit as opposed to one that goes right across the center. Thanks. Sorry to interrupt.
Yep. And in fact, Roy, what the model I just said was best. I was able to get a better score by having a more triangular. You know, this is a little. I started out with something like this, but in fact, this, you know, you might say this fits a little better with something like that, right?
Right.
So the time of a flat dip, the maximum dip is shorter because of that grazing angle. And again, you'll all remember that, actually, if I can do this, put a link in the new tab. There we go. Oops, where's that new tab?
Left more.
There we
More.
go. There we go. That if we enlarge that and then tilt up, right, it's only going to be fully over, and this one isn't, this is so tilted it's not fully over the whole time, right, but for a shorter period, whereas if this were going straight across, right, then the period during which maximum dip is a much longer period there. So, hey, this is the problem. Anyway, so it'd either be a longer period, maximum dip, or shorter, depending on that tilt. And so from these numbers, this you can actually calculate, if we go back, you know, go back to the math we did in the modeling lab, we can calculate the size of WASP-43 from this data. And I don't know if any of you have done that, but so if we do 1.171 minus 1.133, the difference there is 0.038, but that's not the percent difference. To get the percent difference, we want to divide that by what was 100%, which was 1.171. So I'll divide that 0.038 by 0.1, whoops, sorry about that, 0.038 divided by 1.171. That doesn't look right. Sorry. 0.038 divided by 1. 171. There we are. That looks better. So it's a 3% dip. And you'll remember that it's the square root of that that's going to be the ratio of the size of the planet to the size of its star. And so by taking the square root of 0.03, we have WASP-43 being a planet that's 0.18, nearly 20% of the size of its host star. So it's very big, you know, a larger than Jupiter-sized planet that you can actually get an estimate for within the data lab. And that is what students would fill in here. And as Jim is pointing out in the chat, he often has to remind his students that this is the relative size of the planet to its star, although not to our sun. So, so if this star happens to be smaller than our sun, the planet might not be as big as 2 times the size of Jupiter. That's exactly right, Jim. And in fact, you'll remember we gave that link on the ExoLab community that goes to data for all the stars. You can check in the NASA Exoplanet Archive. Although again, there's this question, you don't want to go to the published data until you've figured out what your own results are, right? Because results are results. Are there any questions about how to calculate the size of your planet from your light curve, your best fit model? Okay. And again, on page 6, we actually have Roy created this little animation that visualizes the size of your planet compared to its star. And if you press Z, when that, I just pressed Z, it'll stop. And then you can see that depending on what this percent dip was, the size, the relative size of the target planet to its star is different. And you can see we're comparing over here to Jupiter, Earth, and the Sun. And so you can see that given the messiness of our data, it would be very hard to detect an Earth-sized planet with our little 6-inch ground-based telescopes. Because even a planet this big, which would have a dip like this, I'm not sure that our messy data would be able to distinguish that. So that's something to point out why we put telescopes like Kepler and soon TESS in space to detect transits of Earth-sized planets. This is very hard to do from the ground with all that atmosphere and moon and all that other stuff getting in the way. As Roy just talked about, your model, depending on whether the orbit is tilted or edge on, the shape of that curve really can give you some information about that. And just by choosing one of these, it's entered in the student's database. So I would say WASP-43 is relatively tilted. And I could explain why I think that in my findings chart here. And then the next thing that your transit indicates is some information about the distance of the planet from its star. Now, a single transit is, typically you would want a couple of transits in a row, and then you would have the period. You would know the time for the planet to orbit once. And so we really only have kind of a partial indicator of that by understanding that the duration of that planet to go across the disk of a star, if we assume the star, and again, we have to assume the star is the size of the sun, then we could make some assumptions about what an hour and a half means for a planet to go across something that's, 100 times the size of the Earth. Again, our Newton's or Kepler's laws are telling us that if the planet is closer, it's going to be faster. And so we know this is a close planet with only a duration of an hour and a half. Now, depending on the level of your students, you could either assume a sun-like star and actually do the calculations based on the orbit, or Roy's provided on page 9 this little graph so that you can do a qualitative comparison to our own solar system. So if somebody were looking at a Mercury transit or a Venus transit from far away, a Mercury transit would take about 8 hours, a Venus transit would take about 11 hours, and the transit of WASP 43 here seems to have taken less than 2 hours, so it's way down here. And if I read it off this chart, that's saying that the radius of this orbit is less than 10 million miles, less than 5 million miles. It's really like maybe 2 million miles away from its star. So much closer than the orbit of Mercury. So there's two different ways. The teacher's guide actually walks you through the calculations if you wanted to have your students actually use math to use a single transit duration to derive an estimated distance. And so the last page of the data lab kind of summarizes students' data. And next week, when we have, or in our next webinar, which we'll talk about when that will be at the end, I'll go over more about how you can look up what your students have in your database, in their database. But the My Findings page kind of summarizes what they've written down about the particular star that they've found, and gives them a quick visualization of this. Okay. I just wanted to kind of give a quick overview of the data lab, but I want to try and make sure we have plenty of time for Shani. So any questions at this point? I did post an assignment on the, kind of an assignment, on the Moodle, on the ExoLab educators community, of some Cotter 2 data for you to do these calculations and try and take a look at the results for yourself, and you can take a look at that. But without further ado, I want to introduce Shani Nava, a grad student at the Center for Astrophysics at Harvard, and working on exoplanet atmospheres. And Shani, I'll let you say more about yourself and your introduction, and I'm going to stop my share so you can start yours.
Okay, sounds great. Let me get this sharing screen figured out.
All right.
Okay, are you guys seeing this?
We are.
All right, so yes, I am Shani Nava, and I'm a first-year graduate student at the University, or excuse me, not the University of Montana. I'm at Harvard now. Get used to that. Originally from the University of Montana, and I'm working with Mercedes Lopez Morales, and she is primarily exoplanet atmospheres. I'll talk to you about how my project relates to atmospheres, but it's a little different. And basically, I'm probing, as it says here, the density relation or density period relation of small exoplanets. And that picture that you see on the left is the Harps North Observatory. La Palma Observatory, and that's on the Canary Islands in Spain. And then that picture is just an artist rendition of an exoplanet, probably a rocky, habitable one. Okay, so up at the top there, I just kind of tried to put in a little bit more general terms what I am doing. And as I say there, I'm measuring small exoplanet densities to investigate how they relate to the planet's distances from their host stars. So if we go back to the total, I said I'm looking at a density period relation. And if we look here, say that I'm looking at how far the planets are from their host stars. And as some of you may know, period and then how far a planet is from a host star, period being how long it takes to orbit the star once, are actually fairly synonymous. So a star that is a planet that's farther away from its star will take a longer time to orbit and therefore have a longer period. So I'm going to kind of refer to those things somewhat synonymously throughout this talk, but I'll try to stay consistent. And the first question that we might ask ourselves when looking at my project here is, why do we care about small exoplanet densities? And we care about small planets, as I'm sure all of you know, because they have the potential to host life, especially if we find them in the correct conditions. And so there are two main conditions that we look for right off the bat to see if something may have the potential of hosting life. And the first one is whether the planet is in the habitable zone around its star. So as you see here, the green planet in the center would be the one in the habitable zone. And this is just the area around a star where it's at the right temperature for the planet to host liquid water. Because life as we know it on Earth, that's the one thing that it definitely requires is liquid water. The second big requirement for a planet to possibly host life is that it be rocky. And so that's why I've labeled this as a rocky Earth-like planet. And, we may make the naive assumption that all planets that are around the same size as Earth are rocky, but that's just not necessarily true. And so as it turns out, small planets we've found come in a variety of compositions, and we can't always assume that they're Earth-like. And so, for example, we have some planets, just like Neptune or Jupiter and, Jupiter or Saturn in our solar system that are these gas giants. And even if they were in the habitable zone, we would never be able to set foot on them. So not much use for life. And so there's a lot going on in this plot, and I just want to kind of talk about, I'll walk you through what's going on here. But the first thing that I want to go over are the axes. So if you look down on the x-axis, can you guys see the slides okay? On my screen, it's blocking the bottom. Can you see the full slide?
Yeah, we don't see all the things that are blocking that you have. We actually see the full screen.
Okay, I just want to make sure. So down at the bottom on the x-axis, we have mass, and on the y-axis, we have radius. And this is actually just a plot that characterizes the different densities of planets. But to know a planet's mass and radius is to know its density. And we will see the most dense things at high masses and small radii. So those are going to be in the lower right, and the least dense things with large radii and small masses. So those would be in the top left. And these curves that you see running through the plots, each one of those curves represents all the different mass radius combinations that would lead to a planet, or that would suggest that a planet had the composition listed. So for example, that top blue curve, if a planet were to have a mass and a radius corresponding to a point on that curve, we would assume that it probably would be 100% water. And here I've only plotted the rocky planets. I shouldn't say this is someone else's plot that I borrowed, but we are only seeing the rocky planets here. And I wanted to do that so you could see these curves and really get an idea for the different compositions that we're looking at. But if I go to the next slide, you'll see there are indeed quite a few things up in that area that, maybe have similar radii to Earth, and then kind of like 1.5 zone, a little bit lower. but aren't necessarily rocky. And so this is important. If we want to look for life on other planets, we don't want to waste our time looking at planets that couldn't possibly host life anyway. So I've told you why we should care about exoplanet densities. I mentioned earlier that I'm specifically looking at the relationship between exoplanet densities and their distances from their host stars. And so why would we care about this? Or why would a planet's distance from its star even affect its density? Well, as it turns out, some of the small exoplanets that we see may have formed similar to Neptune in our solar system. And the way that works is on the left side here, if this solid body of rock and ice builds up massive enough and fast enough to trap gas before the gas escapes the disk that it's forming in, you'll actually see this effect in the second picture here happen, where you're starting to not only have like a rock ice base solid, but then you also have a gaseous envelope that sits on top of the planet. And so what happens is, if these planets are close enough to their host star, so you see the host stars off to the left there, and they get blasted with radiation constantly from this host star, so there's a blast of radiation, it's actually going to cause some of that atmosphere to evaporate off. And this is, of course, something that happens constantly. It's not in little jets like this, the way that I'm showing it. But, the big question that we have to ask ourselves, knowing that this is a possibility, knowing that it's possible that there are Neptune-like planets that have lost their envelopes, is whether these things are, well, I'll get there in a sec. Let's talk about this first. So ideally, if we wanted to understand whether something that's rocky started out as a Neptune, we would just sit on one of these Neptune-like planets and watch it just get blasted with radiation from its star over time and shrink. Unfortunately, we don't have the time to do that because things on the astronomical scale happen very slowly. And so I'll ask you instead to consider a system of planets now that are orbiting the same host star, and they're receiving radiation from their star. And so as we can imagine, as time goes by, the planets that are closest to the star are actually going to lose their atmosphere faster than the ones that are farther away, because they receive a higher flux of radiation from the star. And while we don't get many systems that have this nice set of planets in a row that we can look at, if we look at planets at a variety of distance from their stars that are around many different stars, we can start to kind of compare this relationship between the distance between the planet and the star and the density that that planet has. And that's how we actually get a grasp on whether these things have an envelope or not, is its density. Because if it has the envelope there, then there's some extra gas on top of the solid to fluff up the planet a little bit and to actually make it less dense. But if this thing is pure rock, it's just going to be really dense. So this big question that comes up when we know that this is a possibility is, did exoplanets that we've discovered that are larger than Earth but smaller than Neptune, this sort of class of exoplanets that we don't see in our own solar system, are they cores of, did they form like Earth, rocky, without capturing any gas? They were just pure rock from the start? Or are they cores of once Neptune-like planets whose atmospheres have evaporated? In this effect that I just showed you. So before we can answer that question, what we really need to do is determine the density of different exoplanets. And so I'm going to talk to you about how we go about doing that. So you guys have talked about transits quite a bit, so I'm hoping maybe Kepler has come up. But for those of you who aren't familiar with NASA's Kepler mission, this is a telescope that was launched into space, and it's just sitting on the same patch of sky, taking image after image, looking for these events in which a star's brightness is dimmed, and it's because the planet is passing in front of it. You guys are all too familiar with that, so I won't go into too much detail. But basically, as you just discussed, the dip in that brightness, or the magnitude of the dip in that brightness, is going to correspond to the ratio of planet radius to star radius. And if we know the radii of those stars, then we can just go ahead and get the planet radius. And as it turns out, Kepler has done this for hundreds of exoplanets that are in the category that we're interested in, which is down in this kind of like 1.5 to 3 Earth radius range. So we have plenty of radii to work with. Now we just need masses, because as I said before, to know a planet's mass and radius is to know its density. So that's where I come in. My part of our project is to determine masses for Kepler exoplanets that have already been discovered by Kepler. They already have a radius measurement for them. So now we just need that last piece, the mass piece, to figure out the density and possible composition. And we use a method called the radial velocity method. This is data taken by HARPS North in the Canary Islands, that picture I showed you at the beginning. And basically, this looks for a periodic shift in a star's spectrum that's caused by the mutual gravitation between the star and an orbiting exoplanet. So when a planet orbits a star, the planet also causes the star to wobble a little bit around the center of mass of the system. And we can measure this wobble in the form of a spectrum. So up top here, you see a non-shifted spectrum. This is like, I mean, it could be any species that you're looking at in terms of chemical composition, but we've got some spectral lines here and we know where they normally should fall. And we go and look at the star one day and we see that those lines are in fact redshifted. And then later we come and look at the star again and we see that they're blue shifted. And this is because as the star is moving away from us, the wavelength of the light gets stretched out and it appears redder. And then as it's moving towards us, it actually gets compressed and it appears bluer. Well, if we see this happening periodically, we can actually figure out that there's probably a planet there because that's the only thing that orbits periodically. And we can use this fairly simple equation, which is just the shift that we see in the wavelength, or that spectrum shift I showed you, over the original wavelength we started at. That's equal to the radial velocity of the planet, or the velocity with which the planet is moving away from you in your line of sight and toward you in your line of sight. And as it turns out, once we convert to those radial velocities, the amplitude or semi-amplitude of the signal, this K value right here, actually has a direct relation to the mass of the planet. And so once we determine the radius of the planet and we go and detect it with this radial velocity method, we now have a mass as well. Okay, so how does this all come together? Like, how does it all piece? Because I've told you the pieces, but I haven't told you exactly how I put it all together. So as I said before, I'm determining masses and therefore densities of small exoplanets, but I'm doing it at a spread of distances from their stars. So I've plotted here for you just the distribution of periods for different Kepler exoplanets. And so far, a lot of these planets that are down in the low period area, they have already been characterized. It's a lot easier to figure out masses. If we look, of course, planets that are close to their stars. So if we look back at this slide here, you'll see that P in the bottom of the equation. And that refers to period, which, as I said, is synonymous with how far a planet is from its star. And because it's on the bottom of the equation, this means that things at a longer period will actually induce a smaller K value and therefore be more difficult to find. And so these long period planets out past like 10 days haven't really been characterized much. And they're very difficult to detect in radial velocity signals. And I'm using a fairly new method that uses something called Gaussian processes to actually find these planets and determine their masses from their signals. And so in the end, as I determine masses for more and more small exoplanets that are at a variety of distances from their stars, I'm actually going to continue to populate this density plot that I showed you earlier on the left. And then it also will allow me to confirm or throw out the theory or possibility of these planets that we see that are between Earth and Neptune size being actually Neptunes that have lost their outer atmospheres. And so once we plot this up, it'll just be a simple plot of the density versus the period. And if we do find out that these are indeed Neptunes that have lost their envelopes, we would expect to see that as you get closer to a star, the density is going to increase because these things have undergone more radiation. They have lost more of their envelopes. Okay, and that is it. Oh, oops. I want to leave that last slide up just in case there are any questions.
Yeah, so let me open it up. Thanks, Shani, that was great.
Yeah,
We're getting claps in the chat. Yeah, did you?
Oh, I was just going to mention, I didn't know how much of the actual like data I should go into and how much of my my Gaussian processes like framework that I'm using for data analysis. It seems like a lot of the educators here, like you guys are playing around in the data a lot. So I would be happy to go into that, you know, some other time or whatever, if anyone is more curious about it. But I wanted to kind of keep it more general in the big picture idea of the project for this. So.
Yeah, no, that's great. So we have one question that's come in from Jim asking, isn't time a factor? You know, if a planet's been orbiting long enough, couldn't the envelope already be gone?
Yeah, so that's a really good question. This is something I've been thinking about a lot the last couple of days as I've been writing this presentation. And I think that age of systems would definitely be a factor. So that's something that I would take into consideration when I start plotting these things up and looking for trends. I would think that maybe there would be some way to weight the age of a system, you know, have some sort of variable that's not just the density of a planet, but maybe the density, I don't know, divided by the age or multiplied by the age, something like that, some way of weighting the age. But that's certainly something that I've considered because yes, you're right. If we're trying to compare a system that is much older than another system, we would expect that, you know, maybe some things that you would have expected to see envelopes, now they've gone anyway. So that's a good question.
Yeah. And we have a couple more things have come in here. One saying, could the Earth itself be the result of such a process? Maybe we're a Neptune remnant.
So that's a good question. The reason that we really want to figure out whether these are sub-Neptunes or super Earths, super Earth being rocky, sub-Neptune being left behind from a gaseous planet, is that the remnants of a sub-Neptune probably wouldn't be habitable. So when these things are forming, one of the things that's required to actually be able to trap a gaseous envelope is that you have to be out beyond the snow line, which is the point around a star where water is able to start to condense. And so basically the core of that Neptune is going to not just be rock, it's going to be a lot of ice and other, not just water ice, but other volatiles as well. And so the likelihood that it would be habitable is definitely lower than looking at planets that we know formed similar to Earth. So I think that's one of the reasons that we want to kind of you know, figure out whether things are rocky or excuse me, are rocky, purely rocky, or are rocky and icy left behind, because we don't want to waste our time doing a bunch of characterization of, or not characterization, but looking for life on planets that we know it can't be there.
Right. And Scott is one says it would be neat to see the theoretical plot if there was this correlation of distance versus density. What would you expect? So then as you start to develop your data, you see if it's trending that way.
Yeah, so there's actually a paper that did a theoretical study on it. It's very closely related. It was by Eric Lopez and someone else. I can't remember who the author was, but I think it's a 2015 paper. I can go grab it. It's in the other room. I refer to it quite a bit. But
well, we can post it on our online community.
Okay,
folks,
sure.
so
Yeah, that'd be great.
Mm-hmm.
And that paper actually looks at how many super Earth / sub-Neptunes, whatever this size range of planet is that we're looking at, how many of those we would expect to see given at various periods, given the different sources. So like if it came from Neptunes, they make up this histogram of how many super Earths we would expect to see at each given period range. And then if the source of these planets were just purely rocky, they find that you actually would find an opposite trend when you look at period versus like the histogram of the periods. You would see that at longer periods, you would get fewer planets, and in the other one, you would get more planets. And it goes into quite a bit of explanation. There are some reasons for this. Basically, planets that are more massive are better at holding on to their envelopes. And so if the source of these planets were Neptunes that have lost their envelopes, we would expect to see more rocky planets. How do I say? Closer in, because more of them would have lost their envelopes. Is that right? I don't know. I'm sorry. But I'll put the paper up because it's quite interesting, and it actually gives us something very concrete and testable to look at, and it's a large motivation for my work.
Great. Jim has asked how small these redshifts are, and I know I've heard Mercedes talk about the capability of HARPS to detect really small tugs.
Yeah. So the limiting instrumental velocity right now is something like 0.8 meters per second. So this is like teeny. I mean, insane that we're able to detect these signals at such large distances. And one of the things that makes these really difficult to detect is that with radial velocity specifically, where we're looking at the redshift and blueshift, is that star surfaces are also very active, and they're constantly just spitting material off the surface. And on top of that, they've got these different processes going on inside that cause surface changes in brightness and changes in color as well. And so we see those things in the data. It's not just this beautiful planet signal, the shift back and forth like I showed you. It's actually much messier. And that's actually why, not anyone can just go find these masses. The method that I'm using specifically accounts for that stellar noise. And so earlier who was talking about forcing a signal? I don't know everyone's names. I'm sorry. Was it
Roy? I think.
Roy. Yeah. So basically, in the past, when people have gone and looked for signals in these radial velocity data sets, they've just fit for the planet and assumed that there's some random noise there. But as it turns out, the noise in this radial velocity data is not random at all. It's quite correlated and has to do with the activity of the stars. So I'm actually accounting for that as well in my model. And that's why I'm able to pull masses out that haven't been detected in the past.
So we all have to deal with messy data.
We do, yes. It's just one of the joys of life.
Yeah, excellent. There's a couple of questions related to when the maximum radial velocity is, and I know you have a slide that diagrammed that, and maybe if you could go back to that slide just to
maximum radial velocity, sure.
Right, yeah, so.
Sorry.
Yep, that was it.
There we go, this one. Yeah, so the maximum radial velocity is going to occur when you have the most of your velocity vector pointing either directly away or directly toward you. Right. That's when you see the maximum signal. Right. Yeah, and so here I've drawn this for circular orbits, but you could imagine an eccentric orbit where you could either get really lucky or really unlucky, because you're at periastron, meaning that the planet is moving at its fastest pace, right when the star is moving toward or away from you, that's going to cause this huge signal and it'll be great. But if you happen to hit periastron at a time when the star is moving not at all toward or away from you and actually just perpendicular to you, then you'll end up missing that great signal. So
right. Chani, somebody has asked if we can have a copy of your presentation.
Yeah, definitely. I have no problem.
We can post it on our online community as a resource, and Scott also wonders if there's a YouTube of you presenting anywhere.
There's not a YouTube video of me presenting, but there is. I did an interview with Montana Public Radio a couple of years back, talking about my work with my undergraduate project. So that was also with the radial velocity method. And I think if you just Google my name, Shani Nava, it's one of the things that pops up. Like, it's called In Other Words is the radio show. And I saw here, Jim asked how we account for non-circular orbits. So the data does actually tell us if the orbit is highly elliptical. And basically, whereas here with a circular orbit, you see this nice, beautiful sine curve, you start to get some really strange, odd shapes where, maybe the the star spends a really long time at a very low velocity. And so it's not changing very much. And then all of a sudden, we'll pick up really fast because it goes through periastron, and you'll get this really fast spike, and then it goes down again. And so, oh, I'm sorry, I didn't mean to do that. Yeah, it shows up in different shapes in the data, and I have some examples of that too if you want me to pass those on so you can post them.
Great, that's great. I have a question actually, which is, so obviously we're using our small ground-based telescopes to detect hot Jupiters, and I wondered if you knew, if you could relate anything about your work and this work about the atmospheres to this idea of actually finding hot Jupiters, which we didn't expect in the first place. Is not expecting them related to this idea of a hot Jupiter couldn't last for long? I mean, how long do these last in orbits?
You're wondering why did we not expect to find them?
Yeah.
So hot Jupiters were weird just because we knew where Jupiter was in our solar system, and we had this idea for how it formed where it's at. But then we started looking at these other systems and find these hot Jupiters that are or Jupiters that are right in next to their star. And based on our understanding of how Jupiter formed in our solar system, there was no possible way that those planets could have formed where they are now. And so there are a couple different, ideas, theories for those planets actually migrating in over time or getting kind of slingshotted in because of an interaction with another planet. And so that's something that's still kind of open in the research. We're not exactly sure how those hot Jupiters got from where they must have formed, which is out much farther out in their solar system, to where they are today, which is right next to their star.
Yeah, well, that's really neat too.
It is, yeah. I mean, It's so fun when the data just throws you a curveball like that, and it just throws off everything you thought you knew, right?
Right. Yeah, that's great. So any other questions? I don't see any in the chat box. And if anyone wants to unmute themselves because they can't type their question fast enough, you can do that too. All right. Well, I think we timed this perfectly then. Shani, thank you so much. That was really interesting. I think everybody enjoyed it a lot. And you actually will be on YouTube because we do post recordings of our webinar. So either this one or the one a little later this evening will end up being posted. So we'll make people know, and they can look at the last half of that to get your presentation. Great. So with regard to next steps for the ExoLab community, I'm going to have to work with the team to figure out whether we need to have a different time for our next webinar, because our typical Wednesday afternoon at 3:30 and 6:30, I may not be available for, and I have to, I'm not sure about some other members of the team. So we will be in touch with everyone about next week's, we do want to have some continuing, another webinar to follow up on how to publish your data and how to look at your students' data online, how to, you can actually get into each of your students' accounts to see how they're answering all the questions as they go through the ExoLab. So we will keep in touch about scheduling that webinar with everyone. And for now, this has been great. Thank you, Shani. Thank you, everyone. And we will see you either at 6:30 or at the next webinar.
Thanks a lot.
All right. Bye, everyone.